Hey, okay. So while we're waiting to start, can I ask, uh, have you started the assignment? Have you managed to do some of the questions? Hey, can you hear me well? Am I audible? Yeah, it should be. Okay, let's start. So today's topic is analysis of functions and the what that entails. When you talk about functions, functions have certain properties attached to them. And of course, the properties go as follows. The domain, you want to know the domain of the function, so the possible x values, the range, the possible y values, the zeros of the function, the y-intercept, the odd even. So let's try to demonstrate that. And so try to fit in as much as we can. Oh, okay. So if we look at the graph, so domain is obviously the possible x values. The range is the possible y values. So possible x values, possible possible y values. The these are zeros where the graph meets. So zeros. The y-intercept, of course, this is the y-intercept. Intercept. So odd or even, well, this is a property. Now, this is not odd, not even. Not odd, not even. So odd functions and even functions, they're symmetrical in special ways. Monotonic, well, they have monotonic intervals, certainly, but we wouldn't call this function monotonic. It's monotonic on certain between certain points, effectively. Monotonic means always goes up or always goes down. So that is increasing, or decreasing. Critical points. So critical points is where the derivative is zero. So f is zero. So the critical points is this is a critical point. this is a critical point. So let's label them as critical points. Critical points. Inflection. A point of inflection is where the second derivative is 0. And here, this would be a point of inflection, roughly. That's it. That's the only one. So that's inflection. Inflection. Asymptotes, vertical, horizontal, slant. So we have a vertical asymptote. We have a horizontal asymptote. And we have a slant asymptote, the one that is at an angle. So that's a slant asymptote. Asymptote. Okay. And periodic functions that repeat themselves after certain intervals. So a periodic function would look like this. So f of x plus p equals f of x, where p is the period. Okay. Any questions? Any questions what these words mean? Do you understand the meaning of all of them? If you're not sure about some of them, please let me know. Okay. So when we say we want to analyze a function, we want to go through this list and find as much as we can. We're not required to find everything, but as much as we can to help us draw a graph. Because the final goal is to be able to draw a graph of any function. Now, of course, modern technology is such that you can draw any graph in seconds using Desmos or any other software. But the analysis itself, right? When you won't need to, like, it's not a very practical task to draw a graph. But if you go for a university interview, very often they would ask you to sketch a graph. It's a very common question on a university interview. Sketch a graph, or even a job interview. Well, depending on the type of job that you do, they might ask you to draw a graph because they are testing your analytic skills. So we are developing your problem solving and analytical skills today. So we won't be using well, we can use Desmos to check ourselves, of course. Okay, so let me show you how you would typically approach a function. So you want to find as much as you can about this function. So let's start with the domain. There are no limitations here, so the domain is all real numbers. 2, the range. Now, the range is tricky. It's usually very difficult to find the range. But you can, yeah, I would say don't worry too much about that. We can get there. We can get to it later, right? You're not required to do everything on the list. So the zeros. Well, the only zero is 0, so x equals 0. When x equals 0, y is 0. Y is 0, so that's also the y-intercept as well. 4, what's the next thing? Odd or even. Now, to work out whether this function is odd or even, we find f of minus x. So we substitute minus x, and we get minus x over minus x squared plus 1 James, looks like you're having technical issues. Is everything okay? Okay, so and that is going to be minus x over x squared plus 1, which is minus f of x. And by definition, if f of x minus x equals minus f of x, then it's an odd function. Odd function. Okay, so it's odd because f of minus x equals minus f of x, and that means it has a point symmetry. So it has a point symmetry over point 0, 0 at 0, 0. Okay, then monotonic. Right, to work out whether the function is monotonic, we have to find the derivative. So we find the derivative. Find the derivative. And that you have to use the quotient rule here. So it's going to be 1 multiplied by x squared plus 1 minus x multiplied by 2x, which is x squared plus 1 squared. And get x squared plus 1 minus 2x squared equals x squared plus 1 squared equals 1 minus x squared plus 1 squared. And this is 1 minus x, 1 plus x, x squared plus 1 squared. So you can see that the bottom is always positive. So positive. So we don't care about this one. Now this thing, well, we can work out that it's if x is greater than 1, it's if x is greater than 1, then it's negative. If it's, well, if x is greater than 1, f of x is negative, and that means that f of x is decreasing. So that's what monotonic intervals. This is a monotonic interval. If x is between 1 and minus 1, you can check that this is going to be 1 minus something. That's going to be f is going to be positive, so f of x increasing. And if x is less than negative 1, f dash of x is less than 0, and that means f of x is decreasing. Okay, nice. So from here, we can work out the critical points. So these are the monotonic intervals. 6. Critical points. Critical points. And we've worked out the critical points is when the derivative is 0. So, and that is x equals 1 and x equals minus 1. Minus 1. We can find y as well. So if x equals 1, that's a half, so y is 0.5. And if x is minus 1, y is minus 0.5. Okay, so those are the critical points. And we can quickly check that this is a maximum and this is a minimum. 7, what else do we need? Asymptotes. Asymptotes. So vertical. Vertical asymptotes are only possible if if the denominator is 0. But the denominator is not 0, so there are none. Horizontal. Horizontal. To find a horizontal asymptote, you need to find the limit of f of x where x tends to infinity. Right, so let's do plus infinity first. And that's x over x squared plus 1. If x goes to infinity, well, what we can do is we can divide top and bottom by x, and we get, we can divide top and bottom by x squared. And this is going to be x over x squared over 1 plus 1 over x squared. So it's 1 over x divided by 1 plus 1 over x squared. And this tends to 0, and this tends to 1. So 0 divided by 1 is 0. So y equals 0 is a horizontal asymptote. And similarly, limit of x tends to minus infinity, f of x, is the limit as tends to minus infinity of x over x squared plus 1 is also 0. And that means that y equals 0 is a horizontal asymptote. Horizontal asymptote. So you need to find the limit of the function as x tends to infinity. And, well, it's periodic. No, it's not periodic. I mean, we don't really need to check. We don't really need to check that. So I like to combine this information on a single table. So I draw the axis. I put all the interesting points. The interesting points are the zeros. So 0. The critical point, 1. Minus 1. Oh, I forgot to find the points of inflection. Okay. I forgot about inflection. So inflections, 7, 8 inflections. We just find the second derivative of x. It's not going to be pretty, but what are you going to do? So it's going to be minus 2x times x squared plus 1 squared minus 1 minus x squared 2 x squared plus 1 multiplied by 2x divided by x squared plus 1 to the power 4. Okay, we can divide by that. We can take 2x out. So 2x minus 2x out. X squared plus 1 minus 2 plus, I've taken minus 2, so it's plus 2 minus 2x squared. Okay, x squared plus 1 cubed. So that's going to be 3 minus x squared minus 2x, 3 minus x squared, x squared plus 1, 3. And that so the second derivative is equal to 0 when x is 0. X is plus or minus root 3. So these are the points of inflection. Okay. So I put root 3 and minus root 3. Okay. So first of all, I want to know whether the function itself is positive or negative. The function is positive or negative. So the function is positive here, positive, positive, negative, negative, negative. That's quite simple because you know that. So between the sign of the function, so whether it's below or above the x-axis. Now we know the first derivative. The first derivative is, well, we know it's positive, it's negative, negative, positive, positive, negative, negative. The second derivative, now we know that these are the points of inflection, 0. So to the right, so very positive is going to be positive. So positive, negative, negative, positive, positive, negative. The second derivative tells you whether the function is convex or concave. Right. So here we can draw a sketch of the function, or sort of the behavior of the function. So on this interval from root 3 onwards, f of x is positive, so it's above the x-axis. The gradient is negative, so the gradient is negative, yes. And the second derivative is positive, so it is a convex function. So it goes like this. Between 1 and root 3, f of x is positive, so it's above the x-axis. It is negative, but it is a concave function. So it's like this. Between 0 and 1, it is a concave. It's a positive gradient and it's positive, so it goes like this. So you can see that this is a maximum point. And this is an inflection because it goes from concave to convex. 0, so now the function is negative, so it's below the x-axis. It's increasing and it's convex, so it's like this. Minus 1, so it's negative, decreasing, convex. And here it is negative, decreasing, and concave. Right. So we can clearly see that this is a minimum point. This is an inflection point. Inflection point. So now we can finally sketch the graph. So we put the interesting points 0, 1, root 3, minus 1, minus root 3, 0, 0, 1, 1/2, root 3, well, we can substitute root 3. It's going to be root 3 over 4, so it's going to be quite small. And here we're going to have minus 0.5 and like this. And you can see that the graph goes like this, then goes like this. So here we have an asymptote, right? So we have this asymptote, we have a max, we have a minimum, we have a increasing this. Okay. Does that make sense? Does this, do you understand the method? All right. Let's do another one. No, for an interview, you just find the most interesting ones. So, you would say, you could say that it is an odd function. That means you only need to find the right-hand side. It's a decreasing function. So first it's increasing and then decreasing. And then, yeah, you can work it out. So you don't need to do every step. We're doing a very formal approach at the moment. And the more you practice the formal approach, the easier it will be to do the less formal approach, where you just need to find some of the steps. And yeah, I'll do a mixture. So I'll do some straightforward ones without going through the whole list. I'll do some yeah, right. So let's see how it goes. I've done several webinars on this topic, so please go back to old webinars if you want to see something different from today. So today we're just doing functions, just going through various functions and seeing how you would sketch them without using Desmos. Okay, so this one. Now here we will have a horizontal asymptote. Okay, so once again, we need to find, are there any, well, what's the domain? Domain, again, is all real numbers. So there are no points of discontinuity, so we're not looking for any vertical asymptotes. But if we can find a horizontal asymptote, and it goes like this. The horizontal asymptote is the limit x squared minus 1, x squared plus 1, x tends to infinity. And what I'm doing is dividing top and bottom by x squared. That's a standard procedure. So you do 1 minus 1 over x squared, 1 plus 1 over x squared. So I divide by x squared, and you can see that this becomes 0. This becomes 0, because 1 divided by infinity is 0. And so we're left with 1 over 1. So the limit is 1. That means that y equals 1 is a horizontal asymptote. There are no slant asymptotes, and there are no vertical asymptotes. Nice. What else can we do? Can we find the derivative? Yes, of course. We find the derivative, and this is 2x multiplied by x squared plus 1 minus 2x x squared minus 1, x squared plus 1 to the power 2. And that is 2x cubed plus 2x minus 2x cubed plus 2x. And we're left with x squared plus 1 to the power 2. So that's 4x over x squared plus 1 squared. And we can see that the only critical point is x equals 0. X equals 0 is the critical point. And f of 0 is minus 1. So 0 minus 1 is the critical point. point. You could also notice that this is an even function because f of minus x is equal to minus x squared minus 1 minus x squared plus 1 equals x squared minus 1, x squared plus 1, which is f of x, which is the same. So f of minus x is equal to f of x. That means it is an even function. Now, you can see from here, you can see then if x is greater than 0, then f of x is increasing. So it's a monotonic function. From 0, it's a monotonic function. If x is less than 0, f of x is decreasing. So we can say that it's not just a critical point, it's a minimum. Should we find any points of inflection? Oh yes, let's. So f double dash of x is 4 multiplied by x squared plus 1 squared minus 4x multiplied by 2 x squared plus 1 multiplied by 2x x squared plus 1 to the power of 4. 3, it's going to be 4x squared plus 4 minus 2 to 16 x squared plus 1 cubed equals 4 open bracket 1 minus 3x squared plus 1 cubed. That's equal to 0 when x is plus or minus 1 over root 3. So these are the points of inflection. Okay. So we draw the table. We put the interesting points. So we have 0. We have 1 over root 3. We have minus 1 over root 3. Is that it? Looks like it. Yeah. Okay, so the second derivative. Well, you can look at the second derivative. The second derivative is the function f of x. F of x is x squared minus 1, x squared plus 1. Ooh, the zeros, yeah. We haven't mentioned the zeros. Okay, so that's 1 and minus 1. So zeros plus or minus 1. Okay, so the function is positive here. Positive, negative, 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 positive. You can. It's easy to verify. Just check these intervals. Check any number from this interval, and then you will see whether it's positive or negative. So these are the zeros. Then we have, what do we have? We have the first derivative, and this first derivative, there's only one critical point, so it's increasing. So positive, 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 negative, negative, negative. And the second derivative, it is negative here, negative, positive, positive, negative, negative. And it kind of should be like that because it's an even function. So the first and the second derivative must be symmetrical. And the first derivative must be anti-symmetrical. That's actually a consequence. these are symmetrical, and this is anti-symmetrical, because if f of x is even, then f dash of x is odd, and f dash dash of x is even, and it goes on. It's quite an interesting. It's a very interesting proof. You can prove it, and it's quite cool. Right. Nice. So here, this starts from 1. The function is positive. It's increasing, but the gradient is the second derivative is negative, so it's a concave function. It goes like this. It's negative, it's increasing, it's concave, like this. It's negative, it's increasing, it's convex. Negative, increasing, convex. Okay, like this. Negative, decreasing, convex. Negative, decreasing, concave. Negative, decreasing, concave, so like this. And it's positive, it's decreasing, concave. Oh, nice. So we can sort of see what kind of function that is. And we now can sketch it. So just y equals x squared minus 1, x squared plus 1. So 0 minus 1. Let's do it quite pronounced. Minus 1 plus 1 minus 1, 1 over root 3 minus 1 over root 3. So these are the zeros. Now this is obviously a minimum point. This is an inflection point where the function changes concavity. This is the inflection point. This is a 0, and this is a 0. Okay, so it goes like this. We also know that it has an asymptote. Y equals 1 is an asymptote. Okay, and that's an inflection point. If you substitute 1 over root 3, so it is f of 1 over root 3 is going to be 1/3 minus 1, 1/3 plus 1. So that is actually plus or minus. It's minus 2/3 divided by 4/3, so it's minus a half. Okay. Okay, so this is the function. Yeah, so this is a point of inflection. This is a point of inflection. Okay, y equals x squared minus 1 divided by x squared plus 1. Here it is. So quite yeah, so we have the zeros. We have the horizontal asymptote, as you can clearly see, y equals 1. Y equals 1, horizontal asymptote. And yeah, so not bad. Okay, next one. Next one is a polynomial. So obviously there's no asymptotes. You can obviously see that it's even. So it's even. The domain is all real numbers. The range, we don't like, usually we don't need to find the range because it's usually quite complicated. Okay, let's find the first derivative. So that's 4x cubed minus 20x 20x. Where is that equal to 0? Well, that's equal to 0 when x is 0, or x is plus or minus root 5. I'm just solving this equation. So 4x x squared minus 5 equals 0. So x equals 0. So these are the critical points, critical or stationary points. Okay, so it's a continuous function, so it's yes. So let's find the second derivative. So that's 0, 9. That's the critical points. Root 5. Oh, that's 25 minus 50 minus 25 minus 25 plus 9, minus 16. And minus root 5 minus 16. So these are the critical points. The second derivative, that's going to be 12x squared minus 20. And x is equal to 20 over 12. It's 20 over 12. X squared is 20 over 12. X squared is 5/3 plus or minus root 5 over 3. This is the inflection. Inflection. Do I want to substitute them? Well, let's try. So root 5 over 3. So root 5 over 3 squared, that's 25 ninths minus 10 times 5, 3 plus 9. 50 times 3, 150. 25 minus 150 plus 81 ninths. So that's something. Minus 150 plus 81 minus 44. So minus 44 over 9. And of course, minus 5 over root 3 would be the same. Minus 44 over 9. Yeah, so that's those are the inflection points. And then I quickly draw point. So we have 0. We have root 5 over 3, root 5 minus root 5 over 3, root 5. Okay, we haven't found the zeros, and we actually can find the zeros. So zeros. X to the power 4 minus 10x squared plus 9 equals 0. X squared minus 1, x squared minus 9 equals 0. X equals plus or minus 1. X equals plus or minus 3. So 1 is here, 1, 1, and 3 is here, 3. Okay, so -1. It's a lot of things going on in here, but do I actually need to do the whole thing? I'm gonna skip the table because it's just gonna be too tedious to do every single bit. Let's see if I can work it. If I can work out the whole function. So 1 minus 1. So these are the zeros. -3 and -3. -3. So this is symmetrical graph. 0, 9. So 0, 9 is here. Then what do we want? We want 3. We want √5, 16. √5. So √5 is about 2 and something. -16. And that's a critical point. So that looks like it's going to be a minimum. √5 -16. And the symmetrical point here, minus √5 -16. What else? And then we have √5/3 -44/9. -44/9, so that's roughly -5. So √5, so it's somewhere here and here, and those are the inflection points. Okay, so looks like I can draw. And of course, the fact that I know how a quartic graph looks like. Cool. So let's see if x to the power 4 minus 10x squared x y equals x to the power 4 minus 10x squared plus 9. And indeed, it does look like that. Okay. Moving on. That's an interesting one. I haven't done this before, so I'll do it on the spot. So there are no limitations on OR, aren't there? There are. Because okay, so let's write down sine x, cos x. I'm kind of tempted to say, well, sine is between -1 and 1, and cos is between -1 and 1. That doesn't really help us. So what I want to do, sine x, cos x, I'm going to write it as 1/2 sine 2x, and that is helpful. Because now I can say it's periodic, and the period is a pi. Because sine 2x has half the period of sine x, right? Because it's squished, right? We know that. So if you draw the sine graph and then you draw the sine 2x graph, it's a squished graph, so it's the period is pi. And it's easy to show that. So f of x plus pi is going to be log 2 1/2, well, sine x plus pi and cos x plus pi. We know that sine x plus pi is minus sine x, and cos x plus pi is minus cos x. So you sub them back in, and that becomes log 2 sine x minus sine x multiplied by minus cos x, which is the same as log 2 sine x cos x. So we've shown that the period is pi. Okay. So f of x plus pi is the same as f of x. Right. Now, the logarithm only exists when the argument is positive. So sine x cos x must be positive, because you can't take a log of a negative number. Interesting. So we can say 1/2 sine 2x is positive. In other words, sine 2x must be positive. So where is sine positive? And that means that sine has to be an angle of the first or second quadrant. So from 0 to pi. So 2x must be less than pi, less than, yes, strictly less than, and strictly greater than 0. So x is less than pi over 2 and 0. But of course, it's periodic, so we have to take that into account. So x is in fact less than pi over 2 plus pi n, and less than 0 plus pi n, where n is any whole number. So what does that mean? Well, if n is 0, it's just simply x between 0 and pi over 2. If n is 1, x is between pi and 3 pi over 2. If n is 2, x is between 2 pi and 5 pi over 2. Yeah, okay, etc. So x, the function only exists on these single intervals. Now, but we only need to look at one interval. We only need to see, since the function is periodic, since function f of x is periodic, so f of x is periodic, we only need to investigate it. Investigate between pi over 2 and 0, because it just repeats itself. I hope that makes sense. So let's look at log 2 1/2 sine 2x between x is 0 and pi over 2. So sine x changes sine 2x goes like this. From 0 to pi over 2. Not including, of course. That's y equals 1/2 sine 2x. The maximum value is 1/2. So first the function is increasing from 0. And let's have a look at what happens, what does the log do? X, y. Particularly we're interested in log between 0 and 1/2. So this is 0. This is 1/2. And this is 1. We know that log from goes like this, the log graph, log 2. Okay. So from 0 to 1/2, this is increasing. So this is increasing. Okay. And then it is decreasing. Well, it's decreasing in the same way. So it's going to be like this. Wow. This is fascinating. Okay. So now we want to sketch the graph. X, Y. So we're taking the log of this bit. So log of 1/2 sine 2x. Well, if we substitute 0, well, we can't. And if we substitute pi over 2, we can't, well, we can't. But we can substitute pi over 4. If we substitute pi over 4, pi over 4, so f of pi over 4 is going to be log 1/2 pi over 4 pi over 2, 1 log 2, 1/2 sine 2 times pi over 4 is going to be log 2 1/2, which is -1. Okay, so it's going to be -1 at this point. And then we can investigate what's happening. So 0 and pi over 2 are points of the points of discontinuity. So we want to know what's happening. What happens as x approaches 0? Well, we have log 2 1/2 sine 2x. So x approaches 0, that means sine 2x approaches 0. When x approaches 0, log tends to negative infinity. So this is a vertical asymptote. So as x goes back, it's like this. And as x tends to pi over 2, it's a similar log 2 1/2 sine 2x also tends to minus infinity, because it tends to log 0, and log 0 is minus infinity. So it goes like this. This is a vertical asymptote. We can show that this is a critical point. So is it a critical point? Let's check. Oh. Is it a critical point? Well, probably is. So we find the derivative is 1 over ln 2 multiplied by sine x cos x multiplied by cos 2x. And that's equals 0 when x is pi over 4 is the critical point. Critical point, so that's a maximum point. Yes. All right. And now finally, what we need to do is just to duplicate this graph. And yeah, so the graph looks like this. That's a tough one. I didn't expect it to be that hard. So pi over 2, and then from pi to 3 pi over 2, then from minus pi over 2 minus pi. Okay, so these are all vertical asymptotes. And it's going to have maximum points here, 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 and here. It's going to go like this. Like this. Like this. Like this. So quite a fascinating one. And let's see if that's accurate. Y equals log base 2 of sine x cos x. Ah, it is. So pi over 4 minus 1, 5 pi over 4 minus 1, etc. So this is probably harder than, well, this is probably the hardest thing you can get on an interview, but yeah. They don't always expect you to get it, to get the full thing, but they do want to get something out of you. Okay. Now let's do some with slant asymptotes. By definition, if you want to do a slant asymptote, slant asymptotes. There are two ways you can find them. First is the formal method. Formal method. Y equals mx plus c is a slant asymptote. Where m is the limit of f of x divided by x as x tends to infinity. And c is f of x minus mx Yes. C is the limit as x tends to infinity of f of x minus mx. Yes, lovely. Okay, let's use this formal definition. Of course, you have to consider plus infinity and minus infinity separately, because you can have a asymptote on the right but not on the left, and vice versa. But yeah. Okay, so m, to find the slope of the slant asymptote, we find the limit of f of x, so x squared plus 8 divided by 1 minus x over x tends to plus or minus infinity. And if you do that, so it becomes the limit x squared plus 8 over x minus x squared, which can be written as the limit. We divide top and bottom by x squared, so 1 plus 8 over x squared, 1 over x minus 1. And as x tends to infinity, this tends to 0, this tends to 0, and it's minus 1. So m is minus 1. To find c is the limit of x tends to plus or minus infinity of f of x, so x squared plus 8 over 1 minus x minus, so plus mx, plus 1x, sorry, plus x. Right, so I'm substituting m. If I'm losing you at some point, please let me know. Plus minus infinity, and that becomes x squared plus 8 plus x minus x squared. X squared cancels, and you get 1 minus x. And you can divide top and bottom by x. So that's 8 over x plus 1 minus 1 over x minus 1. So that's equal to minus 1. So c is also minus 1. So y equals minus x minus 1 is a slant asymptote. I won't do the analysis of the function. Let's just draw the asymptote. So we draw minus x minus 1, so it's going to be like this. Okay. There's also a vertical asymptote at x equals 1. So there's a vertical asymptote that's going to go like this. And now, well, there are two possibilities. Positive. So it's always positive. Here, it's always negative. Is the y-intercept. The y-intercept would be 8. Oh, minus 1, sorry. Yes, you are correct. That's better. Thank you. That's y equals minus x minus 1. X equals 1. That's a vertical asymptote. And we just need to figure out, well, if x is negative, it's just always positive. So we need to find the minimum point. So f dash of x is 2x multiply 1 minus x minus x squared plus 8 multiplied by minus 1 divided by 1 minus x squared. F dash of x is 2x minus 2x squared minus plus x squared plus 8. 1 minus x squared, and minus x squared. So minus x squared plus 2x plus 8. X squared minus 2x minus 8. Minus 4 minus 2. X minus 4. X plus 2. So x is 4. 1, 2, 3, 4 is a maximum point. Okay, so there's a point here. So it's going to go like this. And minus 2 here. So the graph will be like this. So that's a slant asymptote. So it's like a hyperbola. So there's an intercept which is 8. 8 is the intercept. So it's like this. That's an asymptote. So basically the graph is squeezed between two asymptotes. That's another sort of classical graph. Let's see how it looks like. Y equals fraction x squared plus 8 over 1 minus x. So that's the graph. And let's draw the asymptotes. X equals 1 and y equals minus x minus 1. So you can clearly see that these are asymptotes, in fact, and yeah. But what my main aim is to show you how to find the asymptotes. And there's the second method of finding a slant asymptote, which is way simpler. So where should I put it? Second method. Non-formal method. 2. Informal method. Informal method. Okay. So you need to use long division. Long division. So you got x squared plus 8, 1 minus x, f of x. It's hard to see. Like you can do just long division. Yes, you can divide the top by the bottom. It's fairly straightforward. Okay, so let's do that. So 1 minus x plus 1. And you have x squared plus 0x plus 8. So minus x goes into x squared minus x times. So it's going to be x squared minus 1x. And then that goes subtract. So it's x plus 8. So minus x, so that's going to be minus 1. And minus 1, so it's x minus 1. And the remainder is 9. So you can write this as minus x minus 1 plus 9 over minus x minus 1 plus 9 over 1 minus x. And that's your horizontal asymptote. I said it's way easier. Just do long division and you get the asymptote straight away. Basically, what does it say here? It says that as x becomes really large, as x becomes to infinity, this thing becomes negligible. As f of x is approximately the same as minus x plus 1. And that's what we call the asymptotic behavior. This is a very physicist approach, and I really like it. It's harder to spot though. Do you understand this method? Do you understand what I did? Excellent. Yeah, so and like I wouldn't even do long division, right? Like let's call it the Vlad method. It's not my method. It's also long division, but it's a slightly different version. So I would do it like this: x squared plus 8, 1 minus x. So I want to divide, so I would write x squared minus x plus x minus 1, and then plus 9. I would write it like this. Why would I write it like this? Well, x and x cancel, and minus 1 plus 9 is 8. But if you divide this 1 by 1 over x, you can write it as x squared minus x over 1 minus x plus x minus 1 divided by 1 minus x and plus 9 divided by 1 minus x. You can split it into 3 fractions effectively. And then the first fraction simplifies to minus x. The second fraction simplifies to minus 1. And the third fraction is 9 over 1 minus x. That's how I would do it if I was doing it. So yeah, and here's your asymptote, because this thing is negligibly small. As x, an asymptote is what happens to the function if x becomes really, really big. And what happens to that function? That the function becomes indistinguishable from a straight line. And that's what we see on the graph. The function approaches a straight line. So that's y equals minus x minus 1. And this is y equals minus x minus 1 plus a tail, plus something. Okay. Lovely. Do we have time to do 2 more? Okay, well, we can do 1 more. Like you can also see here. Here you can straight away do the long division. So it's going to be x cubed minus. Now you need to be careful because it's minus x. So it's minus x plus x divided by x squared minus 1. So that's going to be x plus x over x squared minus 1. This tends to 0. And the slant asymptote is y equals x is an asymptote. And also there are 2 vertical asymptotes, x equals plus or minus 1 are asymptotes. Interesting. Also we have 0, 0 as a point. And I think we can already sketch it. Let's see if we can. If we can sketch the graph. So 1, That's an asymptote. -1. That's an asymptote. Y equals x. That's an asymptote. Now, if the function is positive, it is positive. So it has to be like this. And here it has to be like this. You can use calculus to find the minimum and maximum. And in the middle, well, it's actually going to be like this. It's going to be like, it doesn't change sign, does it? At 1. All right. Now, somebody had probably told you that what is an asymptote? An asymptote is a line that the function gets close to but never crosses. That's not a very good definition because sometimes the graph does cross the asymptote. It just doesn't cross it at infinity, right? So sometimes the graph crosses the asymptote, but not at infinity. At 0, it can cross it easily, right? You can have very many points of intersection, like y equals sine 1 over x has an asymptote, so y equals 0 is an asymptote. And yet the graph goes like this. So it crosses it infinitely many times. Actually, I'm not sure that it does, but yeah, don't take my word for it. I'll delete that because it would be embarrassing if it's not the case. It does cross it, but just not infinitely many times. Probably. Let me see. Sine 1 over x. Yeah, it's different. Of course it is. It crosses it several times. It crosses it infinitely many times, but yeah. Okay. Now, you could have a situation where you have an asymptote, like a horizontal asymptote, and the graph goes like this. It crosses it again, and then approaches it at infinity. All right. The portion from -1 to 1 not decreasing. No, it should be. I'm judging from here because when x is positive, it's positive. Let's check. X cubed. Oh yes, I think you're right. Of course you're right. Yes, it's decreasing. Yes. Because all right. So finally I made 2 mistakes in one question. Okay. Sometimes the graph crosses the asymptote. And let's check. Y equals x cubed over x squared minus 1. Yeah. Here it is. So quite nice. And this one, well, first of all, what we see that there's a denominator and there's a square root. So x squared plus x must be positive. And that means x plus 1 must be positive. So x has to be less than 0, or x has to be greater than, sorry, x has to be greater than 0, or x has to be less than -1. So it doesn't exist on the interval from 0 to 1. Okay. In other words, x does not belong to from -1 to 0. Okay, then we have an asymptote. We surely have an asymptote because we can take the limit of f as x tends to infinity. We can take that as x. We can take x out and we get square root of 1 minus 1 over x. And that becomes 1. So y equals 1 is an asymptote. Okay. So I'm running out of time here. And y equals 1, so that's this. And then it's positive when x is greater than 0. And it's negative when x is less than 0. So 0 and -1 are vertical asymptotes. X equals -1, x equals 0, and -1. So those are the asymptotes. So it's positive here. So it should be something like this. And it should be something like, ooh, minus. Oh, that's the case. When it's plus infinity, it's 1, and when it's the limit as x2 tends to minus infinity is actually -1 f of x. So we have two asymptotes. One is on the left and one is on the right. So y equals -1. So it should be something like this. I'll just draw it. So sorry, I don't have time to do a thorough analysis, although this is a very interesting one. Over square root of x squared plus x. Oh, interesting. Okay, so almost right. I haven't done this one correct. So the left side is correct, but the right side is not. So it's actually like this. Okay. Cool. So that's that. And excellent. All right. I'll see you in 2 weeks' time for some physics. Right. And I'm creating the next maths assignment for you, which is on equations and inequalities. So fun stuff. All right. So see you in 2 weeks' time.